So here we are looking at problem 1537. We are given a balanced chemical equation, and we are told that we are given 0.1 moles of nitrogen monoxide, 0.05 moles of hydrogen, and 0.1 mole of water, and placed in a 1-liter vessel at 300 K. We're also told that through the balanced chemical equation that all of these are gases. So we know that we can include them as concentrations in our equilibrium constant. We're also told our equilibrium concentration of nitrogen monoxide. And from this information, we're asked to calculate the equilibrium concentrations of all the other chemicals, and we're asked to calculate Kc. So in this case, it is going to be, hold on a second. There we go. It is going to be necessary to use our ICE chart, where I stands for initial concentration, or if we're solving for a Kp, initial pressure. C stands for change, which I indicate by X, and E stands for our equilibrium concentration, or pressure. Whenever we use an ICE chart, I always put the balanced chemical equation on top, and every chemical gets its own column. ICE charts will always have 3 rows for initial, change, and equilibrium. To use the ICE chart, we have to be given information in our initial and our equilibrium, or our initial and change, or equilibrium and change. Usually, it is the first and last column that we're given information about. Now, in this problem, we are given information about our initial concentrations. Now, I want to caution you, in this problem, we are given moles, not molarity. But because the volume of our reaction container is 1 liter, our molarity is equal to our number of moles. Okay, so we're given 0.1 mole of nitrogen monoxide, 0.05 moles of hydrogen. We're not told how much nitrogen is given, so if a given chemical is omitted, then we assume that its initial concentration is 0. And then we're given this concentration of water. Now, the middle column is what we have to figure out. There are 2 things we have to figure out. The first I'm going to focus on is the sign. When these 3 chemicals, nitrogen monoxide, hydrogen, and water, are placed into the container, of course, it is not at equilibrium because we have no nitrogen. For the reaction to reach equilibrium, it has to shift to the right so nitrogen can form. Therefore, I know that to reach equilibrium, my concentration of NO has to decrease, as does my hydrogen, and my concentration of nitrogen and water are going to increase. It's very important to determine the sign of our X value. Reactants will always have the same sign, whether it's negative or positive, and products will always have the same sign. And reactants will have opposite sign from products. So that's the first thing you have to establish. If one concentration is 0, then it's easy to know which way the reaction will go. Otherwise, you'd have to calculate Q. The next thing we've got to determine is the coefficients of X. And as long as we have a balanced chemical equation, that is not difficult. The coefficients of X are going to be equal to the coefficients of our stoichiometric coefficients, of our balanced chemical equation. So we have negative 2x, plus 1x, and plus 2x. So whenever we have a table, make sure that your 2 things in your X or your C row are correct, the sign and the coefficient for X. Now in an ICE chart, the last row is always a sum of the first 2 rows. So we sum these first 2 rows together to get our equilibrium concentration of nitrogen monoxide. Same thing for hydrogen, same thing for nitrogen, same thing for water. And then in this particular problem, we are actually given an equilibrium concentration of NO. And let me bring this up a little bit. Okay. We're told that our nitrogen monoxide equilibrium concentration is 0.062 molars. And we have a relationship with X because according to our table, the equilibrium concentration is 0.1 minus 2x. So now I have a linear equation that I can solve. So I subtract 0.1 from both sides and get negative 0.038 is equal to negative 2x. I divide both sides by negative 2 and I get x is equal to 0.019. Now that I have a value of x, I can solve for the equilibrium concentrations of all my other chemicals. And once I know my equilibrium concentrations of all the chemicals, I can calculate K. So now I use the values in my last row to calculate my equilibrium concentrations of the remaining 3 chemicals. According to my table, the concentration of hydrogen is my initial molarity, 0.05, minus 2x. So 2x would be 0.038, and that's my equilibrium concentration of hydrogen. Nitrogen at equilibrium is simply equal to x, so that's 0.019. And then hydrogen, what is this? Water at equilibrium is 0.10 plus 2x, so that would be 0.138. So now I have the equilibrium concentrations, and I was given the equilibrium concentration of NO, which is down here. I didn't have to calculate that. And I take those equilibrium concentrations and I plug them into my Kc value. This is my equilibrium expression for this balanced chemical equation, and I get that my products are in my numerator, my reactants are in my denominator, and each concentration is taken to the stoichiometric coefficient that is in the balanced chemical equation. So once I plug all my values in, I let my calculator do the hard work, and I get 653 as my Kc value.